you are in the right place. Okay. I'm going to teach this course in English, but you are free to ask questions in la langue de Molière. And I will answer with a good quality, and I can even answer in French if you want, but I can also answer in the language of Shakespeare. Okay. So I'm Peter Van Roy. En avance, il n'y a pas de problème, hein? J'ai commencé une minute en avance. Et ça, c'est Mathieu Bigaglio qui sera l'assistant. So he will be the TA, teaching assistant. This is a course about distributed systems. It's okay, I'm early. Before starting, I want to pay a few seconds of respect to the Ukrainians who are fighting for their freedom and for Europe's freedom. Okay, so this is a course about distributed systems. So the first question is, what is a distributed system? So here's a guy who seems to know what he's talking about. He says a distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. So somewhere in the North Pole, a computer fails and you can't use your computer. Of course, you know who this guy is, right? Who knows this guy? You know this guy? He's probably the most famous person in distributed systems. He invented many of the basic ideas and protocols. So a famous consensus algorithm called Paxos. He invented different kinds of logical clocks. He is maybe the one guy who is the founder of the science of distributed systems in the 1980s. So do you know who it is? Leslie Lamport, yes. Congratulations. This is Leslie Lamport, who has recently won the Turing Award, which is the Nobel Prize for computer science. So what I want to do, first let me talk about how I'm going to organize the course. So this is a course on distributed systems, but there's different kinds of distributed systems. So the first half of the course will be about small systems with a small and fixed number of computing nodes. And all of the basic concepts we will learn here. And the second half of the course will be on large distributed systems, like the internet and many systems on the internet. These are systems with a large and variable number of nodes, thousands, millions. And if you have a million nodes, then it's pretty obvious that the number is going to change. There's always a node that's going to be failing, or new nodes that are going to be coming in. Okay, so that's the basic thing. And the first part of the course will be very theoretical. There are some very important concepts. So we're going to dive in and look at the hardest concepts. So you will really understand distributed systems after this course. Okay? That's the point. Okay, let me say something about the organization of the course. So there's a weekly lecture today. It's the first one. There will be lab sessions, but not every week. There will be some lab sessions during the semester, and Mathieu is going to prepare them. There will be lab sessions preparing the midterm. There will be lab sessions for helping you prepare the course project. Okay? So it's very important because you have to do practical things, because otherwise it's very theoretical. You have to get some real understanding of it. And let me say also how I'm going to grade the course. So there is a project, there will be a course project, which counts for 1/4 of the points, and it's mandatory, and you have to do it during the semester, okay? Unless you can show me a very beautiful medical document written by a doctor or something. Otherwise, you have to do it during the semester. There will also be a midterm exam around week 7, probably around the smart week in the middle. This one is also worth 1/4, and there will be a final exam, which is in 2 parts. So together they're worth 3/4, but part of the final exam, you will get the maximum of the final and the midterm. That means if you do very well on the midterm, you already know that you don't have to do that part on the final exam. You will keep your midterm points. But if you do very badly on the midterm, nothing is lost, okay? There's no averaging. Some of my colleagues, they make averages, which is very bad, okay? But what can I say? I can't really say that to them, because each professor is a master of his own course. But I will not do that. So you will get the maximum. That means even if you do very badly on the midterm, or you party the whole year, you can still get good points if you do that part on the final. Okay? And the other part of the final will be worth half. Okay? In terms of the syllabus of the course, for the first half, there is a book called Reliable Distributed Programming, Introduction to Reliable Distributed Programming, by 2 very smart guys, Rashid Garami and Luis Rodriguez. I know both of them very well. They're very nice guys and very smart. And this will cover the first part of the course. Now, this book is not completely necessary. There will be enough information on the slides. Okay, so the slides will be on the Moodle. They will have enough information. But this book is very highly recommended, so I can take a look at it. And there is a second edition where they add algorithms, secure algorithms, so Byzantine secure algorithms. It's just basically a superset of the first one. So that's for the first half. For the second half, there will be the slides. There will be also papers I will give. There's no other text. So the second half of the course will be kind of, depending on what I'm interested in. There's many big kinds of systems we can discuss. Peer-to-peer, gossip-based systems, how to design large systems, things like BitTorrent, and so on. So there's many possibilities for these large systems. So I will pick some of the interesting ones. And we'll see that in the second half of the course. Okay? Okay, so that's the organization. So, Mathieu, you don't have to stay if you don't want to. He knows everything already, yeah? But hopefully you will see him during the semester.
In the lab session.
In the lab sessions, huh? He knows already this stuff. Okay, so today I want to give you a kind of teaser. I want to give you a kind of introduction to the ideas, touch on many things, and then we will dive into the technical stuff. So first of all, what is a distributed system? Well, technically it's a set of computing nodes, like this one, connected by a network, some network protocol, but it appears to the users as a single system, coherent. It means all the nodes are somehow working together and they provide a single functionality to the user. So you don't see that there's many nodes or network, you see one coherent system. Okay? So we're going to study that in a fundamental way, conceptually, with formal models and foundations. So this course is really a combination between theory and practice. We'll talk about lots of practical examples, but there is also a good amount of theory. There are some things that are really important to understand to really understand how these systems work. Okay? So, why study distributed systems? I think it's a little bit obvious, but I will say something about it. It's very important nowadays in society. The internet is already a distributed system. The web, which is built on top of the internet, is also a distributed system. Many small devices, the Internet of Things, which are connected together to the internet, are yet another distributed system, or a bunch of distributed systems. So there's all over the place, okay? Distributed systems are all over the place. Also, technically, there are new ideas here that you have not seen before. Very important new ideas, and in order to get scalability, so the system is large, can be very large. How do you get a system to work if it has millions of nodes? Also, the reliability. How can you get a system to be reliable if nodes are failing? Also, inherent distribution. If I am here and my friend is 1,000 kilometers away and we want to work together, how do you arrange that? Okay. So here's an example of a system where you have a place where you have many computing nodes together. Here's an older example. So this is the space shuttle. This is something already from 1980s. The controlling computer on this is actually 4 computers, 4 nodes connected together because of fault tolerance, and there's a vote. Okay? All the 4 computers are running exactly the same program, and they have to give exactly the same result. And if you have that, then you're happy. But if one of them fails, you still have 3, and you're happy also. Actually, no, you start panicking if one of them fails, because if one of them fails, maybe the second one can fail, who knows? Okay, so this is important for fault tolerance. Okay? So what is so challenging about distributed systems? Well, the first thing that makes it a challenge, of course, is concurrency, which you have already seen in courses where you, on a single processor, where you can have multiple threads, multiple processes. Here we have multiple computing nodes, all executing independently of each other at the same time. You have to program then a very concurrent system. Okay? But that's the easy part. Okay? If you thought this was hard, now we get it a next level. We go to the next level of hardness. We're introducing a new thing that makes it even much harder than just regular concurrency, which is partial failure. If I have a system with many nodes, 20 nodes or 50 nodes, and if a node crashes, it can crash or it starts doing weird stuff. We want the system to keep working, okay? Even if a node crashes. This is called partial failure. Part of the system fails, and the rest keeps working. Now, this is not usually what happens on a single program. If you run a program in a process on a Mac OS or whatever, if the process crashes, everything crashes. Okay, so that's easy. Either everything crashes, but in a distributed system, things are not so easy. It's very, very frequent that part of the system crashes, and the rest has to keep working. Okay? So concurrency, so let me say a little bit more what it is. So you have many nodes, they're all executing simultaneously, so in parallel, and you have messages traveling between them. Asynchronously, which means it takes time when one computer talks to another, but we don't know how much time. It can vary. It's asynchronous, so there's no real-time bounds. So we will see later what this means precisely. Okay? So this is, if we forget partial failures, this, if we only look at systems where nodes are executing in parallel, this is called parallel computing. And this is what scientists love to do, like physicists. They have what's called grids with 10,000, 100,000 nodes. They do very complicated numeric simulations, okay? That is not distributed computing. That is parallel computing, because in a system like that, you basically, essentially don't have failure. All the nodes are sitting in a big, nice air-conditioned room, and they are reliable and they don't fail, okay? And the purpose is to do some kind of very fast quantum chromodynamic computation or whatever. So in CERN, for example, the big physics lab on the Swiss-French border, they do a lot of this. But this is not what we are going to do. We are going to do more. We are going to do distributed computing, which is not the same, which adds partial failure. Okay? Partial failure, it means the network can fail, messages can be lost. You can have partitions, where half of the system is not talking to the other half. Okay, for example, because there's a break in the middle. Humans have this too. If your brain consists of two lobes with a bridge connecting them called the corpus callosum, if you cut that, you have two brains in your skull. Two individuals are living together in one skull. So this is an example of a network partition in a human. Okay. This actually, humans can keep living like this. Okay. We are very fault tolerant. Also, of course, you can have node failures. And computers can fail for many reasons. They crash. They're always crashing all the time. And that's very normal. It's not exceptional. Failure is a completely normal situation. So we have this highly concurrent parallel system where the messages are traveling. We don't know how long it takes, and sometimes it fails. This is the system we're programming. Okay? You can see that it's maybe challenging to program a system like this. Okay? This is exactly what we're going to study today and in the rest of the semester. Okay, so you can see that. So how are we going to address this? Well, we are going to do step by step. I'm going to introduce a programming model, a simple programming model, a kind of multi-agent model that is essentially the best way we know to program these systems. We will build them in layers, where each layer is very simple and can be understood. And eventually we get to something very sophisticated. But we can't do a sophisticated thing in one step. We have to do a small step at a time. And today I will introduce this to you. So today is kind of an overall summary. There are certain kinds of problems that appear that always, over and over again. One problem is, for example, that the nodes have to agree on something. Okay? If we're collaborative text editing, well, all the users have to see the same text, even though they're updating it. So agreement is a problem that happens over and over and over again. Okay? And this is called a core problem. And there's other kinds of core problems. So what I want to show you today is some of the core problems and give you some intuition. Okay. So this is another principle of this course. So we're going to see a lot of theory in this course, but the theory is always connected to intuition. So whenever I introduce a new theory, a new theoretical concept, try to get the intuition. There's always intuition there, okay? So I'm going to tell you the intuition. Sometimes it's on the slides, sometimes not. If it's not, then you should react. There's intuition everywhere. So I am not a mathematician, and especially not a formalist mathematician who doesn't like intuition. Intuition is how we understand things, okay? The formalism is there to make sure you don't do stupid things, but the real thinking happens in the intuition. Okay? So you see the connection between the two. So I'm going to start by giving you an intuition. And this is a famous problem called the two generals problem. So we have two generals. In fact, they're attacking the city. They're on the hills opposite of the city. And they are in the same army. They're the same, and they're attacking the city. So the city could be Byzantium, for example, and the two generals are trying to together coordinate their attack. Okay? So these two armies have to attack the city in the middle. Now, the city, of course, is defending itself, and the city will, it has a strong defensive army. So the two generals, they will only win if they attack at the same time. Okay? Simultaneously. So they have to agree on the time. Now, this is happening in ancient days. There was no radio communication or something like that. The only way they can communicate is by sending messengers. So a messenger is a human holding the message, running and trying not to get killed on the way. Okay, the messengers might be captured, tortured, killed, whatever. So there's no guarantee the messenger will arrive, and we don't know how long it will take. Maybe they have to find another path, hide. It might take a long time. So you see now how does it work? How are the generals agreed? Well, let's try to solve it. Let's try to find a solution. Two generals. So I call them G1 and G2. Okay. Okay. So G1 proposes an attack. We attack at 5 o'clock on Sunday morning. Okay. And he sends a messenger to G2 saying, I propose this time. Fine. G2 receives the message. Fine. But how can we be sure that G2 received the message? The messenger might be slow, or he got killed and tortured and whatever. How are we sure? Well, G2 can send another messenger back to acknowledge, and yes, I received the message. Okay? And when G1 receives that acknowledgement, then G1 knows that G2 got the message. We're good. But how does G2 know that G1 got the message? You see the problem, huh? You start seeing there's a problem here, huh? Okay, so G2 is not sure. So G1 now is sure that G2 got the message. But G2 is not sure that G1 knows that it received the message. So G2 is not sure. So how do we ensure that G2 knows that G1 received the acknowledgement? Well, G1 sends an acknowledgement of the acknowledgement, of course, back to G2. But this acknowledgement of the acknowledgement might get captured too. You see, there's a problem here. Huh? It seems like there's no solution. I mean, it's not obvious, the solution to this. How do you make sure? In fact, there is no, you can prove, in fact, there is no algorithmic solution in this case. Okay? And this is important in a distributed system. This problem is impossible to solve. Okay? So this applies to distributed systems. We have two nodes. They need to agree. They're communicating by messages on a channel. But the channel is unreliable. The messages might be dropped. And of course, we also don't know how long the messages take. Okay? So this is a distributed system. Okay? For this system, okay, you want an algorithm for this. Okay? So agreeing is a core problem. It's something that always comes back. How do we solve it? Seems not so easy. All right. So what do we do? Okay. So let's make it more formal now. Okay, so this problem is called consensus. This is one of the fundamental problems of a distributed system. So usually you can have more than 2 nodes. Okay, you have n nodes, and they all have to agree. So all nodes propose a value, but sometimes nodes might crash, stop responding. Oh, what's happening? Okay, and the algorithm must ensure several properties. Okay, so now we want to be very precise, because whether it's possible or impossible depends very, very precisely on the conditions. Okay, if we change a little bit one of the conditions, maybe it's possible. So this is a main theme in this course, that whether something is possible or impossible, or efficient or very slow, depends very precisely on what the underlying network can do. Okay, so here we have to be very precise. So all correct nodes, so those are the nodes that don't crash, have to decide eventually. Eventually means after finite time. Okay, so the word eventually will come back over and over again in this course, and it has a very precise meaning. It means after some finite time, but we don't know what it is, but all we know is finite. All nodes will eventually decide. Of course, they have to decide the same thing, otherwise it's not agreement. And of course, they only decide on values that were actually proposed. Because otherwise it's easy. They can all decide 0, okay? But nobody proposed 0, but they decide 0. No, that doesn't work. They have to decide only on proposed values. So you have to satisfy these 3 properties. It turns out the difficulty is making all 3 of them. You can always just satisfy 2 of the properties. Okay? For example, all nodes eventually decide, and they decide the same. But you forgot the 3rd one. Okay? Well, that's easy. They all decide 0. Or all nodes decide, and they only decide on proposed values. But forget the 2nd property. Well, each node will decide on its own proposal. Okay? Because they don't have to decide the same. Or if you forget the first one, each node decides the same, and they only decide on proposed values. Fine. Then you just kind of broadcast, and some of the nodes maybe will get the value and decide, but all nodes will not decide. Okay? So 2 out of the 3 is easy. The real problem is all 3 of those properties. Okay? Okay, so you can see the kind of problem we're going to solve. And this one seems not so obvious on an asynchronous network where messages can be dropped. It seems maybe it's impossible, huh? I mean, the 2 generals problem gives us intuition that it's maybe not so easy. Okay? This intuition is correct, huh? Okay, so consensus is a very important problem. Here's one example which everybody uses all the time, which is databases. So almost everybody here, probably everybody has a bank account. Well, the bank stores your information of how much money you have in a database. And in order for it to be reliable, that database has multiple copies. Okay? And even these copies will not be in the same building. Because if that building burns down, then both copies are destroyed. No, the copies will be spread apart, far away. But when you take money out of the bank, those copies have to agree on how much money you have left. Okay? Even though there might be failures. You see, that's very important, huh? Otherwise, the bank doesn't work. So this banking algorithm. Databases will use what's called transactions. So you have already seen the concept of transactions, but a transaction happening on a distributed system, it's not just one copy of the data. You have many copies, at least two, and usually many more, and they all have to agree. So the transaction has to use a consensus algorithm, so they agree. This is called atomic commit. So either they all agree and the transaction commits, or they don't and the transaction aborts. It's possible for a transaction to abort. Huh? If you cannot get them all to agree, it aborts. And if you have to try again. Okay? So you can see this is an important problem. Huh? Consensus is a real life thing that's very important. And when I buy something on Amazon, okay, I don't want to add too much advertising for Amazon because those guys are slave drivers, but I buy something on the internet and I use my credit card. Money is transferred from one place to another. So at the end of the day, it goes to a bank, and we have this happening. So the whole of internet commerce is based on consensus. So how does that actually really work? Because things can fail on the internet. You have seen it happen. I think everybody has seen things failing on the internet. But still, the money has to stay good. How do we do it? Well, that's something we're going to talk about in this course. Okay? So consensus is an important problem. You can see that up. Let me give you another one now, which is broadcast. Okay, broadcast is different from consensus. Broadcast is where I send a message and everybody has to receive it. For example, everybody is watching a movie. That's a kind of broadcast. But let me talk about a very specific kind of broadcast called atomic broadcast. So this is a strong kind of broadcast. So one node broadcasts a message, okay, and the message is sent to all the other nodes, and then there are properties. So let me define now the precise properties. So if the sender does not fail, so we say the sender is correct, all nodes that do not fail, we call them correct nodes. So a correct node is a node that does not fail during the algorithm. They will all deliver the message to the user of that node. Okay? They will also all deliver the same messages, clearly, otherwise it's not a broadcast. And there's a third property, which is why we call it atomic broadcast. Messages are delivered in the same order. So why is that important? It's not always important, that they're delivered in the same order. If I send a video to 1 million people, the frames of that video are broadcast. If the order changes a little bit, that's not important because if a frame is dropped, because the video, even though it's not completely precise, it will still be shown. But sometimes the order is important. A simple case is, for example, in the database, if I add 10 euros to my account, and I broadcast that to all the copies, fine. But let's say I add interest. I add 1% interest to my account. I broadcast that. Those two messages should arrive in the same order. Because if I add 10 euro and then add 1%, then the 1% will also be 1% of the 10 euros. Okay? But if it's the other way around, then the 1% will not see the 10 euros. So sometimes it's important, especially when we're doing very precise things. For example, we are doing navigation of a space probe. There's many actuators, and the probe is maneuvering, and there's a controller controlling all the actuators. Well, they should all do their maneuvers in the same order. Otherwise, things might go very wrong, okay? So the order, the same order is sometimes important, okay? So this is a typical kind of a core problem, a broadcast. And you can see this is a strong version called atomic broadcast. You don't always need it, but sometimes you need it. Now let me tell you something that we're going to do a lot in this course. Atomic broadcast and consensus are the same thing. They are the same, actually, in a fundamental way. So remember I talked to you about broadcast, where consensus, where all the nodes have to agree. And then I talked to you about broadcast, where I'm broadcasting messages, and they're arriving on many nodes in the same order. Those two problems are actually the same. They're exactly the same. They are equivalent. So this is maybe not obvious. Okay, so what's the intuition of this? Well, it means that if I have an algorithm that solves atomic broadcast, I can use it to implement consensus. And inversely, if I have an algorithm, a library or whatever that does consensus, I can use it to implement atomic broadcast. Okay? So, in a very easy way. So the two problems are essentially the same problem. Okay? What's the intuition? You see this kind of what the intuition is here? Can you get what the intuition is? Okay? Well, let me show you one direction. Every node broadcast. So I'm assuming I have atomic broadcast implemented, and I can use it to build consensus. How do we do that? Well, every node broadcasts its proposal. Now we have to agree, but they will arrive in the same order. That means all the nodes will receive those proposals in the same order. That means they will all get the same one first. The first one will always be the same. So the first one they receive is the thing they agree on, because the messages are received in the same order. You see the trick here? See how we're doing it? Atomic broadcast has a very strong property. The messages are received in the same order, and we use that to force it to do consensus. So you can see, if we have an algorithm that does atomic broadcast, we can actually build consensus. See that, huh? See how that works? What about the other direction? I have now an algorithm, a running piece of code, that implements consensus. It means all nodes propose, you run the algorithm, and they will all decide on the same thing that was one of the proposals. Well, I'm telling you now, if I have that, I can actually implement atomic broadcast very easily using that. How would I do that? So when I put a little d here, it means that you guys are going to give you the answer. So how would you do that? Assume now I have a consensus algorithm, piece of code running, tested, bug-free. With that, I can implement atomic broadcast. How do I do that? What do you think? Anybody have an idea? How can I implement atomic broadcast? Well, you have to think, what is special about atomic broadcast? What is the thing that makes it strong and special? Why is atomic broadcast? What is special about it? Huh? The real special thing is this thing, huh? Messages delivered in the same order. That's what's special about atomic broadcast. Okay, if we have consensus, can we somehow do that? We have a consensus algorithm. An idea? How can we somehow do some kind of a clever thing that all the messages will arrive in the same order by using consensus. How can we use consensus for that? Yeah?
And the consensus for every step of the message, for example, if we have a pre-message,
Okay.
we step in order, we have first a consensus, and the first message, a consensus.
But we don't, that's not so easy because two nodes will do a broadcast. One will broadcast A, the other will broadcast B. How can we be sure one of it is before the other? How do you know?
I think we can either token the information who have the token that the next node can do broadcast.
Sorry, say again, how would we do that?
On the message and the token that
A token.
yeah, token say that which node can do broadcast next time.
So how do you manage this token then? Who has the token first? So you're saying the token somehow determines the order, is what you're saying? If I have the token, I broadcast, and then the next person has the token and they broadcast. So how does I have two nodes now. One is broadcasting with the token, and then the node gives the token to another node, so you're saying, and then the second one broadcasts. How does the third node know that they should first get the one from the first one and then the one from the second? How does it know? It receives two messages. How does it know which one is first? No? How? How would you think? I mean, yeah, it's an interesting idea, but you have to develop the idea in your head. How do you know then the order of the token? You don't know. Okay, well, what about it? Yeah, the problem with the token is that you still have the same problem of the ordering, yeah? I mean, the token does not solve that. It only says who sends before the other one, but it will not guarantee who will receive first, one before the other one. But it's going in the right direction, okay? The idea is it's not yet a solution, but it's going in the good direction. You have to look at what we have and what we need. So consensus, we have consensus. We have it, it's running. It's very powerful. Consensus is like a very strong machine, okay? It will guarantee that they all decide on the same thing. We have that, okay? And what do we have to do? This is what we have to guarantee. That the messages are delivered in the same order. So what we have is a very powerful machine that can force the nodes to decide on the same thing. And what we want is this. So what is the thing they should decide on? Now I'm giving you a little bit hint, huh? What is the thing? We have something that can decide on anything, in fact. You can send any data structure to the consensus algorithm. Huh? All the nodes, they will just send any piece of data, and they will all decide on the same piece of data. So what does that piece of data have to tell me? What does it have to tell me? I'm pointing to what it has to tell me. Huh? The data tells me what? It tells me what, the data? Don't look at my hand. What does the data tell me? What does it tell me? There's a word in red there. So each node proposes what? An order. Yes. And then they will decide on a thing which is the same for everybody. But what is that thing? It's one of the proposals. But the proposals are proposed orders. So the first node says, well, I propose that node 1's message arrives before node 2. Yeah? So I broadcast. So you have this algorithm. So node 1 is a naive broadcast. Node 1 sends a message to everybody. Node 2 sends a message to everybody. But they can arrive in any order. So node 1 will receive first 1 and then 2. Node 2 will receive 2 and then 1. Node 1 says, well, actually, the 1 message should be the first one. And node 2 says, no. The 2 message should be the first one. How are they going to resolve this conflict? By running consensus. Yes. You see how it works? So each node, they will just broadcast using some naive broadcast algorithm that just sends everybody, but the order can be any order. 1, 2, 3, 3, 2, 1, 2, 1, 3, whatever. But each node proposes what the order should be. It should be 1, 3, 2. And they run consensus. And the consensus will make them agree. So they all will agree 1, 3, 2. And then, once they agree, they will, this is the algorithm, it's a library, yeah? They will pass 1, 3, 2, in that order, to the application running on top. So the application sees atomic broadcast. See how it works? The fact that the consensus can make you agree on the same thing means you can agree on the order. You see the kind of thinking we're doing here? You get it, right? You see what the idea is here? So, the thing we're agreeing on is the order now, okay? Because a consensus algorithm, you can propose any value, which means any data structure, anything. Well, what you can propose is a list of messages in a given order. And the consensus algorithm will agree on one of them. And that's going to be the order. That's it. Now you have atomic broadcast. Yeah?
A question is that, is the order correct? Does that mean that the consensus...
There's no notion of correct order. The order has to be, this is what atomic broadcast does. Huh? All node will send messages. Maybe you say that the one who sends it first should arrive first. Now that's what you're thinking of.
Yeah.
But is it really so important? Here, it doesn't really matter because the network can be very slow, you see. So we can't really guarantee that the node sending first will arrive first.
But, if you have a consensus algorithm, then why can't they just agree on a clock and then base the order on
why can't they? Very good question. Why can't they just agree on the clock? Tell me, how are they going to agree on this clock? In order for them to agree on the clock, what do you need? Consensus, you see? That's a very good question. So why don't they just have synchronized clocks, hardware clocks, all these nodes? Yeah, fine. Yeah, that would solve it. But how do you get the clocks to synchronize? You see? You need them to agree on the same time. Now it's this time. How do you get them to synchronize? Well, you need something like consensus again. You can't get around it. You see how it works? So this is intuition. I'm not giving you a mathematical proof today. But you see the kind of thinking we have to do. Real distributed systems are like this. Okay? They have these subtleties. Okay? So atomic broadcast is equivalent to consensus. So here I give you the intuition. We didn't see the actual code. We will see the code. And it will be not so hard. So I'm telling you, it will not be Java, okay? Or even Oz. It will be a very special kind of a model, layered, kind of multi-agent model. In this model, the code will be simple. Okay? And that's amazing, huh? In fact, you could ask the question, why aren't all programming languages doing this model? That's a really good question. Why aren't they? They should be, in fact. Maybe someday. Okay? So we're going to see the actual code for this, huh? The theory and the code. And you will understand why things are like this. Okay? Okay, let me go now to another aspect, the concurrence of this system. All these nodes doing things at the same time. Just thinking about it gives you headache, right? I mean, doesn't seem to be very simple. Well, let me give you some intuition of how we solve this. So what does it mean, actually, that all the nodes, and there's a network, are running at the same time, and messages are passing, and slow or fast, whatever? Well, we have to make a precise definition, okay? So the basic definition, the basic system, so it's like the foundation. When we write an algorithm, we're assuming something on the network and on the nodes. So the basics, the most simple distributed system is one where you have no assumption whatsoever. And this is called an asynchronous system. So an asynchronous system, so you have nodes sending messages, and there's no bounds. It means the message, when I send a message from node 1 to node 2, it will arrive, let's say, but there's no bound. It means it might take a long time, years, or maybe microseconds, or milliseconds. We don't know. All we know is that it's finite. That's a very weak assumption. Actually, the post office has that assumption. You sometimes read articles in the newspaper, the letter that was sent in 1912 has been delivered in 2020. Have you ever, I've seen articles like that, huh? It means that the postal system is essentially asynchronous. There's no bound on the delay. I mean, usually letters arrive in 1 or 2 days. Sometimes they take a lot longer, okay? So this is an asynchronous system. Also the computation time, there's no bound. Your computer can be very slow or very fast, you don't know. So this is the weakest distributed system. And you can imagine that writing an algorithm on this system is hard, okay? Because the system does not help you. The asynchronous system will not do any of the work for you. It's the weakest kind of distributed system, okay? Now, in a first approximation, and, oh, this is a weird comparison, but okay, now you see the slide. The internet. So we're going to study the internet. In the first approximation, internet is like that. Okay? If you look at TCP, there's no guaranteed delivery time. I mean, you have had courses in networking, right? And if I send a packet, or using IP, or whatever, UDP, IP, from one node to another, the protocol has no built-in timing, delivery. It's kind of best effort. If the network is very slow, it will be slow. If the router makes it go through fast network, it will be fast. So maybe the message that takes 1 microsecond today will tomorrow take 100 milliseconds. Maybe that's what happens. So there's no bounds, even if it's reliable. So in a first approximation, the internet was actually designed like this. The original TCP design, and even today's version of it, it's asynchronous. It's best effort. It tries to do it as best as it can, but it all depends. Okay? So you see, this is the very first kind of distributed system. The asynchronous system, and it's the worst one. If you want to write an algorithm on top of this, you're screwed in a sense, okay? So if the internet was really like this, we would be royally screwed, if I can say it like that. Then we wouldn't be able to do anything. So the internet, it's sort of like this, but luckily it's not completely like that, as we will see. So we're kind of saved by the bell, in a sense. So in fact, you can prove that consensus is unsolvable in an asynchronous system. That means the algorithm that I showed you, where all nodes propose, you run the algorithm, and they all agree on something after some finite time. You cannot implement such an algorithm if your system is asynchronous. Why not? Well, it's the same as the two generals problem, basically. Okay? And the problem is failure. If even one node might crash, it's unsolvable. Okay? So if all the nodes are totally reliable, it's solvable. But they are not. So even if one node might fail, it's unsolvable. So asynchronous system is the worst. So one of the themes of this course is how do we survive if we have this? So we have to define other kinds of distributed systems. Okay? So the internet is, it seems to be kind of like an asynchronous system. Now, if it was really an asynchronous system, we would be royally screwed, okay? Because the internet would be useless. But it turns out the internet is not completely asynchronous. It's something different. It's something we'll call partially synchronous, which we'll explain in a little while. Okay? So consensus is unsolvable in an asynchronous. So basically, if I can write it here, let me make a spectrum. Asynchronous system. This one is actually the worst. But on the other side, we have a really nice system called synchronous. Okay? These are the best. When I say worst, I mean it's the hardest to write algorithms for this. Best means algorithms, writing algorithms is very easy. Okay? So the other system from asynchronous is called a synchronous system. Now this one is where you do have bounds. The system is helping you a lot. So when I send a message, I guarantee it will arrive in 0.5 microseconds. And I'm guaranteed that. Oh, that's really, really nice. And if I want to do a computation, I know this algorithm will run maximum in 10 milliseconds, no more, for sure. That jet is using synchronous algorithms, okay? So this is the best kind of distributed system. It's the best. It's very easy to write algorithms for this kind of a system. Because, for example, failure, it's very easy. If I send a message from node 1 to 2, and the message does not arrive in 0.5 millisecond, then I am absolutely sure there was a failure. I know for sure, because it's a synchronous system. So that's the easiest, okay? Now, synchronous systems, they do exist. The internet is not synchronous, There's no bound, known bound. But small systems can be synchronous. For example, multi-core. This little guy is a MacBook Pro M2 Pro, which is a very nice one that I just got a few weeks ago, so I'm very happy. It has 19 cores in there, so it's actually a distributed system. And these 19 processors are connected. They are each sharing the same memory, in fact, so they can communicate. And this memory system is fast. And it's a small piece of hardware, it's all in one chip. So I know for sure, for example, that sending a message from one core to another, it might, I mean, I don't know exactly what the number is, but it's some very small number of nanoseconds, okay? And I'm guaranteed. And a cluster is a bigger system. Huh? A cluster is basically a number of processors with a backplane, very high performance backplane. So kind of multiprocessors, small multiprocessors like in boxes like this are usually clusters. They also have guaranteed network performance. So they're also synchronous, known bounds on time to deliver. And a local area network, like an Ethernet, also, you know how long it's going to take, okay? Because you see the wire, and you know that the signal will take so much time. You know how much time the adapters will take. And you know what, if there's a conflict, you know how that's going to affect it. So basically, you know exactly how long it's going to take, okay? So the intuition is that small systems, like multi-core or cluster, which is a small thing, like small box, can be made synchronous. But large systems like the internet, no. Speed of light, routers, failures. The Earth is a kind of big place. Sending a message to Japan, for example, that's like what, 8,000 kilometers? That's a long time for a computer, right? Even the speed of light is 300,000 kilometers per second. 8,000 is 8 over 300, so it would be tens of milliseconds. That's a huge amount of time, okay? So if I have to do many round trips, it's very, very slow. Okay, so big systems will be asynchronous, and small systems can be made synchronous, like a multi-core, okay? Of course, the simple, naive solution would be saying, yeah, just make the whole internet synchronous and we're done, okay? Well, it's not so easy. If you try to make the internet synchronous, you will slow it down by quite a bit. Because what is the bound? Well, the bound is basically the longest time it takes. The bound would be tens of milliseconds. That's a very big bound if I have a system running inside of one building or in one city. Yeah? So if you want to make the whole internet synchronous, it doesn't work. You have to live with the asynchrony, okay? So you see, life is not so simple, okay? Okay, now before making the break, let me just say one thing. If I have a synchronous system, consensus is very easy. It's so easy. Consensus is so easy in the synchronous system. Even if I have many, many crashes, if I have a system with n nodes, up to n-1 crashes, I can do consensus. Of course, at least one node has to survive. Okay? So how does it work? Well, first of all, if I have a synchronous system, it's very easy to detect when somebody has crashed. So every node sends a message to every other node, and the time is bounded. Remember? 1 millisecond, for example. If I don't get a message within that time, I am absolutely sure the node has crashed, because my system is synchronous. So a synchronous system essentially has perfect crash detection. So I know exactly who crashed, and so the nodes that don't crash, it's very easy for them to agree, okay? For example, there's many ways, but for example, every node has a number, an ID, MAC address, whatever. Well, the one with the smallest number is the one that decides, that's it, it's so easy. So consensus is very, very easy in a synchronous system, that's one side, and it's very, very hard in an asynchronous system. It's impossible, okay? So we go from very easy to impossible. Now, of course, the big question now is, what about the internet? The internet is not synchronous. If anything, the internet is in this area. So what do we do about the internet? Okay? What do we do about the internet? So this synchronous, it's so easy. Of course, this is not useful for internet. So the question is, what do we do for internet? Well, that's a good cliffhanger, right? So I will stop here and make a break. Okay, so we finished before the break, and I told you that synchronous is very easy to make distributed systems here. Consensus is very easy, whereas asynchronous is much harder. In fact, it's impossible to make consensus here. And because the asynchronous system doesn't help you at all, it gives you no bounds, whereas the synchronous system is helping you a lot with the bounds. Okay? Now the question that I want to address is, what do we do for the internet? So the internet, in a first approximation, is kind of asynchronous. So if the internet was truly an asynchronous system, then this course would be all over, and I could tell you guys to go home. There's no more things to learn. But luckily for us now, the internet is not completely asynchronous. It's something a little bit different. Okay? So let's study the internet now. Because this is for this course, I'm going to give you the intuition on really most important and the hardest problems. Okay? We're going to go straight to the hardest ones. So the internet, let's look at how the internet is built. Now it's mostly synchronous. So what does that mean? Well, if I have two computers talking to each other, there's a network, and as long as they don't go outside of their little bubble, it's very fast, okay? The bounds are respected most of the time. But if they go outside of their bubble and they have to talk to Amazon, and let's say the Amazon server is in Brussels, then they go into a bigger bubble, and things slow down, okay? So the bounds are respected most of the time, but occasionally, so once in a while, they're violated. And for various reasons, it can also be because of congestion or failures. So congestion is when the network link is overloaded. So this slows down a lot the communication, also failures. So if you look at the two computers talking to each other, like this, they're actually, as long as they talk to each other, they're in this bubble. Let's say the communication is 1 microsecond. This is good. As long as they stay in this bubble, it's like a synchronous system. But assume they have to talk to another computer, which is outside of the bubble. So this one, for example, is Louvain, although probably it's more than 1 microsecond. Here we have Belgium, okay? So this one is going to be in Brussels, for example. Then let's say that it's 1 millisecond. So that's kind of reasonable. So as long as they stay in Belgium, there's another bound, 1 millisecond. But maybe they have to go even farther than that. Maybe they have to go to New York or something, or New York City. Okay, well that will add you, I don't know, 30 milliseconds. So you see, the internet is a hierarchical kind of a system. Okay. As long as you stay inside a particular bubble, it's exactly synchronous. But if you need a service that goes outside that bubble, then you go into a bigger bubble, so your bounds get worse. But still synchronous. Okay? So you see this hierarchical structure of the internet. Why is it like that? Why is the internet like this? Well, in order to understand that, we have to talk to physicists, because now we're talking about how the physics, how communication works, speed of light, limitations, and so on. Distance is the thing, geographical distance. Okay? So as long as you stay within your bubble, you satisfy the bound, but when you leave the bubble, you break the bound, but you get a new bound, which is a bigger number. And there's many bubbles now. There's many levels of this. Huh? So here I show just 3, but there's probably dozens. And if you have studied the internet, you know there's something called autonomic systems. Maybe, I don't know. I will give this subject to my colleague, my esteemed colleague, Olivier Bonaventure, who is a very smart expert on networks. He's actually world authority, and he has implemented actual internet protocols running by millions of people. So he knows very well how this stuff works, much better than me. But it's hierarchy, you see? And as long as you stay within one level, you're synchronous. But sometimes you have to leave that level. So how do we model this? So luckily, it's not completely asynchronous. We need another formal model. And this is the model we're going to introduce. So this is a model that's, in some sense, halfway in between synchronous and asynchronous. It's called partially synchronous. And this is a very important concept. The invention of this concept is what made distributed systems practical on the internet. Without this concept, we couldn't do big applications, okay? So again, this is due to Leslie Lamport, okay? The partially synchronous system. So how does it work? So today I'm going to give you the intuition of this, but later on we'll see more formally, and we'll see how the algorithms use it. So it's like this. Initially, we assume the system is asynchronous. It's very, very bad. We assume it's really bad, asynchronous. But eventually, which means after some time, it becomes synchronous. So some magic happens, and we have bounds. So initially, the idea is we don't know the bounds. Computers are talking to each other, we don't know the bounds. But maybe the bounds, eventually we know them. Let's say we think they're 1 microsecond. But no. We talk to Brussels, actually it's 1 millisecond. So eventually, we somehow, the algorithm that we run, knows what are the true bounds. So initially we don't, and eventually we do. So this is it seems very vague, but it's a very precise thing. It means when you start running the algorithm, you know nothing about the bounds. After some finite time, you know that bounds exist, but you don't know their values. Okay, which is funny, yeah? And you know that there is some such finite time. Now this can seem very strange, but hopefully after, when we get more into it, you will get the intuition of this. With this, we can now do consensus again. If we have this, if we have a partially synchronous system, now we can do consensus. Remember, for asynchronous it was impossible. For synchronous, we could do it very easily, up to n-1. But for partially synchronous, it's very funny. We can do it up to n/2. That's funny, yeah? In fact, not exactly n/2, just less than n/2. You can crash. In fact, the real condition is that the majority must be correct. So somehow, the majority of the nodes can impose their will, in a sense. As long as the majority does not crash, then you can actually have a consensus algorithm. So if you have 10 nodes, for example, 6 must not crash. You can only allow 4 to crash. If you have 11 nodes, then 5 are allowed to crash. It has to be the majority must be correct, because the majority is 6 in that case. If you have that, you can actually implement an algorithm to do consensus. Okay? The first person to do this algorithm was Leslie Lamport. The algorithm is very famous. It's called Paxos, and it was around 1989. This was the first major advance in the area of distributed systems. Okay? So this is a thing we're going to talk about in this course. We're going to see how does partially synchronous, it basically solves all the problems in practice. Okay? So this is useful for internet. So this is something that we discussed, but I mean, we've been discussing it, huh? What it means is that if you have these hierarchical bubbles, in the beginning, when you run your algorithm, you don't know where you are. In fact, while you run the algorithm, you might actually have to go to a bigger bubble and make a worse time. Huh? You might have to. But eventually, that process stops, and you have reached the maximum bubble, and so you have a bound. Okay? So the hierarchical structure of the internet fits the partially synchronous systems. Okay? Okay, so that's an intuition. So in this whole discussion now, I've summarized a lot of things. Okay? And this will take us several weeks or half of the course to really understand what's going on. But I hope that this will at least gives you the intuition of it. Huh? Okay. Let me say a little bit more now. Let me talk a little bit more about failures now. So now we change topics a little bit. The new thing in a distributed system compared to concurrency and threads is failure. Okay? So failure is going to be a big thing in this course. So the first, what we're going to do is we have to encapsulate it. We have to master failure. Failure, how do we model it in our algorithm code? And this is another major discovery or invention in distributed systems, is the concept of a failure detector. It's like a black box that tells you whether there's a failure or not. If you assume this kind of a black box, so it's a system component that detects crashes. But it's like a black box, so you don't really care how it's implemented, but inside of it, it's doing things like heartbeats. It's doing back and forth and waiting to see whether there's a failure. And it can sometimes make mistakes. So maybe it thinks the node fails, but it didn't really fail, it's just slower, okay? Because you move from one bubble to the next. Maybe the failure detector thinks that it's 1 microsecond bound, but it's actually 1 millisecond. Well then, the failure detector can correct its mistakes. It can start by making mistakes, but after a while, it stops making mistakes. So that's very important. The system can start by being wrong, but eventually it's right. Okay? It's a little bit like real life. If you don't understand something, well, eventually you will understand it. Is the point. Okay. So this is an important thing. With this concept, the code becomes really simple. I told you concurrency is already complicated. Adding partial failure in the so this was invented in the early 1990s. Before that, the code for distributed algorithms was really, really complicated, hard to understand. It was research level. You had to be world expert to understand. So the stuff that world experts were publishing in the 90s, we're going to see that here in this course. We're going to see many of those algorithms that used to be state-of-the-art that only world experts could understand. We will see them one after the other in the week. So this makes the code very simple, okay? Concept of a failure detector, okay? So we're going to show the code. It's solvable, but the point is the code is actually simple if you have failure detectors, okay? Okay, this is what we will see in the course. And now, to finish today, let me talk about some different kinds of failures. So failure is the new thing, really, compared to concurrent programming. So we have to understand failure. This is important. In real life too, failure is important. So how can nodes fail? Well, the most simple failure is just a crash. Crash stop, which means the node is working normally and just stops working. At some instant in time, it's like it's not there anymore. It's like a computer that just crashes, it just stops working, okay? Or you have a network cable and you just cut it. It just stops working. But that's a very simple kind of failure. I want to give you some intuition on different other kinds of failures, okay? And I want to show you the two extreme cases. Okay, so it's important to understand what are the extremes. Like here, asynchronous and synchronous are two extremes, and we're sitting in the middle. Well, the failures I want to show you also two extreme cases. Byzantine faults. This is the worst kind of failure. Part of your system is permanently bad. But when I say bad, I mean evil. The nodes are not just crashing, they're actively trying to break the system. They can be very smart. They can collude. So they're like enemies, okay? Part of the system, the nodes are arbitrarily doing bad stuff. That's Byzantine faults. Okay? But it's only part of the system, luckily. So if I may, let me make a comparison that is not politically correct. The Trump supporters in the US are basically mentally ill. But as long as they are a minority, then the country can still run. Okay? This is kind of like a Byzantine fault. Part of the system is permanently bad, but as long as it's small enough, the rest of the system can run. This has been studied. Okay, so that's one more extreme case. The other extreme case is what's called self-stabilizing. In this case, the whole system can be really bad. Could do any weird kind of stuff. But it's only temporarily, like temporary insanity. It's like you go crazy, but it's only a short time, and after that you're back to normal, and you try to fix all the damage you did, okay? So those are the two extreme cases, and algorithms have been written in those two cases, okay? So let me give you some intuition on that. So Byzantine faults. Some nodes are basically behaving arbitrarily, so they're running any kind of code, arbitrary code. They're not just crashed, they're actually running code, but evil code, arbitrarily bad. They can send wrong information, they can try to forge things, they can do all kinds of bad stuff. They're hostile, and this is the kind of algorithm you need when you want to do something like a cryptocurrency, Because you have nodes talking to each other, but money is involved here, real world money, okay? So there's a big incentive to steal that money. So there's going to be evil nodes that are doing exactly that are trying to steal it. So how can Bitcoin guarantee that nobody will steal it? Well, they use Byzantine algorithms, okay? They use cryptographic techniques. So a Byzantine algorithm is able to tolerate arbitrarily evil nodes as long as there's maximum 1/3 of them. That's very weird, But it turns out if you do the mathematics of these algorithms, like Byzantine consensus, as long as 2/3 of the nodes are good, honest, law-abiding citizens, the 1/3 of the evil Trumpy nodes will not be able to overturn the system. Okay? So that's Byzantine. Notice the algorithms that I showed you before the break were not Byzantine. They were, the consensus I explained before was in the case of just basic crashes and there's no hostile nodes. Okay? In that case, you can actually tolerate more failures. It turns out for partially synchronous, you can tolerate up to half. Huh? Okay, so this is interesting. Huh? If you need Byzantine, you need more honest nodes to make the system work. Okay. The other case is self-stabilizing. This is algorithms that temporarily can go insane, but then they become normal again. Okay? So the whole system might temporarily be in a totally weird state. Okay? So here we are assuming that the code is always the same. It's just the memory, the state, can be totally wrong. Okay? So we call a good state is legitimate state, and a state that's not good is illegitimate. And then there's some kind of mathematical property. I'm just going to give you some intuition on this, and I'll give you an example. So you need two properties. Huh? If you're in an illegitimate state, so arbitrarily insane, then if you keep running, you will eventually get back to a legitimate state and go back to normal. And if you're in a legitimate state, you will stay there. So these are two mathematical properties you have to prove of your code. Okay? So these algorithms are sometimes very useful and has been used in practice. So they don't need to be initialized. That's interesting, huh? Because you just start up the system. You don't care what state it's in. It'll eventually get back to normal. You can combine them. If I have two blocks connected, if one of them is sending junk to the other one, well, the first one will eventually start being normal, and then the second one will be normal, okay? So they're very robust in a sense. So here's a practical example. This is called the token ring algorithm. So this is a famous algorithm that was a competitor to Ethernet, invented by IBM for communication. So these are computing nodes. So how does it work? Well, there's a token. So back to the guy who mentioned the token. Who was the guy who was talking about a token? Yes. So here we have a token, okay? And the thing is, there should be exactly one token circulating, and it's always circulating. And if I want to communicate from one node to another, I wait until the token arrives to me, and then I'm allowed to communicate. And if you do that, you're guaranteed there will never be any conflict. Okay? Now, of course, in the real world, you can have weird things happening, cosmic rays or whatever. Sometimes you can have multiple tokens, so that's not good, huh? I'm running on this thing. Or 0 tokens. This is what you want, the one token. So if I have more than one token, actually the code running on all these nodes is a self-stabilizing algorithm. And any number of tokens, 0, 2, 3, whatever, this algorithm will guarantee that you will always go back to one token. And it's actually not so complicated algorithm. Okay, so this was an important invention in the distributed algorithms. This was not done by Leslie Lamport. This was done by another famous guy called Edsger Dijkstra, also around very early on in the 70s. Okay. So this is this token ring algorithm. I'm not sure if it's really still used, Olivier. It may be the case that Ethernet has one, but in the 1980s, this was an algorithm that was used in industrial systems. Huh? Okay. Now, let me talk a little bit about the future, what's going to happen in this course, but also in the world of distributed systems. Okay? So far, everything I explained to you now is running in this piece of the course. Huh? A small fixed number of nodes. Here we introduced partially synchronous, okay, failure detectors. So this is running here. So far I have not really talked about the system with a large and variable number of nodes. Okay, so let me say a few words on that. So these dynamic systems are very common today. So in these systems you have a large number of nodes, hundreds of thousands. So the most famous ones are the file sharing systems, starting from Napster. You heard of Napster? But then that turned into BitTorrent and all kinds of variations, second generation, third generation, Nutella, and so on. All these file sharing systems are basically peer-to-peer systems, which means they have no server. All the nodes are equivalent, and they're just talking to each other randomly, random neighbors, and there can be hundreds of thousands of them. And of course, these nodes are the nodes of people at their homes, in their houses, who are doing file sharing. Okay, we assume that they are only sharing files between people who have legally bought the copies, right? They're not doing anything illegal in this spot. But so they're sharing files. But how many nodes are in such a system? Well, anybody can connect anytime. They can leave anytime. Also, the systems can crash. So the number of nodes is always changing, and changing very fast. Okay? And this is very reasonable. Huh? If I have a system with 100,000 nodes, it would be very weird if that number was exactly the same always. Huh? So this kind of system, very naturally, the number of nodes is always changing. And still it's working. And it's sharing files, and it's doing nice stuff. Huh? So we're going to see these systems in the course too. And the most powerful of these systems are called gossip algorithms. So the gossip algorithms, it's completely random. It seems completely random. The nodes are talking to each other randomly, connecting to each other randomly. Nodes can be failing or coming in randomly, and still the system is doing some useful work. Okay? So this is very important, and there's many such systems today. And probably you have experience with them. I mean, one of the most famous ones is BitTorrent and all the evolutions of BitTorrent. Probably many of you have used BitTorrent, no? Or some Azureos or whatever, some file sharing thing, okay? So there's many of these. Skype also used to use this before it was bought by Microsoft. Now we don't know what it's using, it's secret, but in those days it did. Peer-to-peer gossip algorithms. Also cloud algorithms. So this is, you would have to take the course on cloud computing. But these are algorithms running inside of data centers, and they are doing things like large data analytics. But data centers are very strange things, because the nodes in data centers are failing all the time. And the reason is that usually there's no air conditioning inside the data center. Why put air conditioning there? You put in so many computers, and they're all running very hot, and they're all very cheap. No name, Taiwan PC clones, whatever. Very cheap, and they're always failing. And so what happens if they fail? Well, you just take the rack of the failed ones, you put in the new rack. That's the economy of scale. So there's always failure happening in there, and there's a very large number of nodes. So all these analytics tools are extremely fault tolerant, even if you don't really see it. And the final one, Internet of Things. This is edge computing. This is all the little devices that are surrounding us. So the most common ones are mobile phones. I see one right over there. Billions in the world, but there's many other kinds of edge devices. So those are all running these kind of systems. Okay. Okay, so let me quickly summarize what we saw today. First of all, distributed systems are everywhere. So it's kind of strange that you have to wait until the 4th year to learn about them. It should be much earlier, but what can I say? I'm just a lowly computer science professor who has very little influence on when courses are taught. So they're everywhere. It's very important. So we're going to study them. So one of the important issues is the core problems. A second one is the internet. Of course, we're going to focus on running large distributed systems on the internet, which is a partially synchronous system. We're also going to talk about failure. Failure is super important. It's happening all the time. And maybe I have a chance to give you some lectures on some new stuff that's coming on large-scale distributed systems. So that would be in the second half of the course. Huh? Okay. So that is the end of the teaser. So we have still a few minutes, but I'm not going to present that much, but let me just tell you something. A few things. So starting next week, we're going to dive in and be a little bit more technical and more scientific and really understand what's going on. So there will be a little bit more theory, but still a lot of intuition. So we're first going to give a formal model of a distributed system. So what is a model? Well, model, that's a set question coming in science. Huh? So you basically take the real world, which is infinitely complicated, and you abstract away and talk only about the properties that are important for you. So we are going to simplify reality and introduce a really nice model of a distributed system that we will use to really understand what's going on. Okay? So this is science. So you will be learning how to do science. So of course there's many courses that introduce models. Huh? And maybe let me do a few more slides and then I'll finish for today. In the engineering curriculum at this university, you have seen many continuous models, at least the engineering guys, differential equations, analysis, continuous mathematics, Well, for this course, forget continuous mathematics. We're going to talk about discrete mathematics here. This is something which you see much less, but unfortunately this is actually much more important for computers. So the models of distributed computing are going to be all discrete. I'm going to reason discretely. And let me maybe stop at this slide. It's not so easy to pick the right model. Huh? It's actually very hard, and it took a lot of effort before people invented this partially synchronous idea, which is a very strange mixture of something precise and something vague, but it's the right one, okay? So this is very hard. So this is something, maybe you learned something in this course. We're going to do impossibility proofs. We're going to show certain things are impossible, like consensus on an asynchronous system, okay? So the 3 C's, we have to, nothing is missing in our model. The model makes no mistakes, it's correct. And it's also simple, concise, okay? So the model is saying all it has to say without making mistakes. Okay. So this is, I think we're 6 o'clock. Let me stop here. Next week, we're going to go into modeling distributed systems. So it'll be a little bit more mathematical, but hopefully all the intuition that I gave you now